Hello everyone, welcome back to Land Alpha Physics. I know it's been ages since I've done one of these videos. The last time I did was refraction, which was ages and ages ago, so as I remember. And we're on to the next topic, which is going to be the topic of waves and wave motion. So in fact, these are the couple things we're going to be talking about. We're going to be differentiating, not mathematically, but as in knowing the differences between longitudinal transverse waves as well as mechanical and electromagnetic ones. We're going to learn this thing called wave speed, frequency, which is met before, and a new quantity called wavelength, as well as just a couple other different kinds of waves and how we can treat them using mathematics. So before we actually go on to any of the mathematics, we have to understand what a wave is. And in fact, if you think back to simple harmonic motion, you might remember seeing that simple harmonic motion is to deal with sine and cosine waves. And in fact, that is essentially what a wave is. It's just a path taken by an object which is undergoing either periodic or simple harmonic motion. So we're actually going to go into a lot more depth about these waves, both how we can sort of expand them mathematically as well as how we can utilize them in sort of some real life scenarios. But as well, we actually need to know parts of a wave before we start going into any good detail with it. So I'll just get my laser pointer. So we can see the point 1 is known as the amplitude, and it's the distance from the point of equilibrium, so when there's no of a particular quantity, either displacement, velocity, or acceleration, because we know if we differentiate either of them, it's just going to be a translated sine curve. But in this case, it might be position. So this might be the furthest a pendulum might be in its swing, is represented by 1. And in fact, we call these either maximas or minimas in proper maths. However, there is actually a name for them in waves, and those are crests and troughs. So a trough is the lowest point of the wave, which we know is the minima, and crest is the maxima. And in fact, the wavelength is the distance between two identical points on the wave. Now I have to be a bit clear with this. I did actually record this before, but I wasn't happy with it, so I'm kind of re-recording this. So if I just select, I can't select an eraser. I'm going to do that. Okay, whatever. So, in fact, what I mean by this is from two identical points, is that it wouldn't be the distance from, say, the origin to another point where it crosses the axis. The reason for that is that the derivative, or the slope of a tangent to that point, also has to be the same. So we can see here, if I just draw, you can see a tangent to that point is kind of going up. Oh, there we go, isn't that good? That's not erasing, okay, whatever. So that's going to be our first tangent. However, if we draw a tangent to this point, we can see that, well, that's a really bad one, but you can see that the tangent directions are not the same. Therefore, we cannot define the distance between this point and this point to be a wavelength. We can see over here that the wave is actually starting to rise again. So therefore, the distance, or rather the wavelength, is the distance between the origin point and this point here because they have the same derivative. And in fact, the symbol that we give it is part of the logo of this channel. It is given the symbol lambda. You can think of it as the Greek L, and it literally just means the length or distance between two identical points on a wave.